we stopped last time starting to work in two specific effects of things. Now, just as a reminder, if we go through and pull up your handout that we were working with last time, so what we've got, remember, we go through with we were working with a one-way repeated measures, with a one-way repeated measures ANOVA design. Now this, the worksheet we have set up here is our ungrouped test that we did, or our unordered means. This is the sort of rate friendship ratings. And so we go through, and on our output, right, we identify our test of sphericity. We always know that we're going to just assume that we violated sphericity, so we're going to just ignore that probably. Within subjects test, we're going to ignore that because that's a different thing that we're looking at, or excuse me, nope. I eliminated that off your worksheet. Was the multivariate test that we're going to ignore on the outcome. But for your test, what we're going to look at is our test of within subjects effects. And so, Lauren, what's our interpretation of this output based on our test of our within subjects effects here? Yeah. What difference is it exactly?
The friendship ratings.
Right. You were just saying, so we're just with this one-way test, right? It's just saying that we're getting, there are differences somewhere across repeated ratings across different vignettes, right? All this is saying is that yes, we have a main effect of rating or whatever it is that we label this factor that's saying that across 8 different vignettes, people are rating, or the mean levels of ratings are different across individuals, right? And so then we've got our twin subjects effects. That's just saying that people are overall different, which isn't terribly exciting. And then we've got our marginal means right here in our graph, right? So we've got, that was our unordered means. Then we also had a test where we went through and looked at ordered means, right? This is data that we collected from psychiatric inpatients, and we're just to give them every couple of weeks, we're just testing their depression scores, right? This is a different type of test because we're expecting the order of those assessments to make a difference. In the last one, we could jumble around the order of those vignette ratings. It doesn't make a difference. Here, we've got ordered means, and so the order in which these are coming along start to become important. So again, we've got our descriptives. Here's our multivariate test. This is a multivariate test that we ignore, right? We're not worried about that. Our sphericity, we assume that we violated that. Then we've got our test of our within subjects effects. And Katie, what's our test of within subjects effects telling us? Right. So we're seeing here that somewhere in these data, just if I'm looking at this and nothing else, right, I know that there are some differences in average depression scores over the course of these 4 assessments that we've done, right? So again, it's really simple. Like these effects, all it's saying is that across repeated assessments, at least one assessment is different than the other, right? Same type of thing that we were talking about with our twin subjects ANOVA, we're just looking at a repeated measures factor, right? So across repeated assessments, one of those is just different than the other one, and that's all we know, right? Now, if we go down through and we take a look at our plots of our marginal means here, we get a good sense for what's going on here, right? We've got a really clear, and thinking about what the data are doing, right? And that's always an important thing, to start thinking about what's the design, how were these data collected, what did this mean, and this makes some sense, right? We see that people, on average, are showing pretty marked decreases in scores over the course of intervention. But again, the order of this starts to become important. We can't just put the score at week 4 and week 6 and baseline in the middle. So remember to identify, sort of, does this make sense? Does the ordering make sense? And is the ordering important given the nature of the design? Okay. So, any questions about the general omnibus test that we're working with here? Okay, cool. So we had started, or ended up, we were talking about, so we got our omnibus effect, right? And our one-way design, our omnibus effect is saying that these repeated, the means, our sample means across repeated measures are different somewhere, right? But now what we need to do is we need to go through and start to figure out where those are at, right? What's going on. Different things we can do. We can talk trend analyses, linear contrast, comparisons, some exploratory stuff. With these designs, these are really complicated designs. There's just a lot of stuff going on with these. And so what you want to make sure that you've got a game plan moving into this, right? You want to, on the front end, say, okay, within this analysis, what am I expecting to turn out? What would make sense? How am I going to go through and approach this? Because if you don't have any type of game plan, it's going to be really overwhelming. You're going to be confused because there's about 7,000 different things that should be tested here. You want to have a good game plan going in so that you know what's going on. That game plan going to be determined by your specific hypotheses, sort of conceptual types of things that you want to be thinking about, how you design your study, the number of type of effects you have observed. All of this is going to come into thinking about how am I going to approach this, right? Getting your omnibus effects is easy. That's like falling off a log. What's hard is getting in here and figuring out exactly what's going on and how to interpret those omnibus effects. Okay, so we talked about per comparison error rates and family-wise error rates. Again, we want to make sure that we are correcting for the possibility of increased and aggregate error over the course of 1,000 different tests, as you'll see as we go through some of these examples. If we're just going to run through and go nuts and just start testing stuff, we could have 20, 30 different ways that we can go through and test something, right? And we need to have some sort of control for that, right? So this is part of our game plan. How are we going to approach this, and do we need to account for aggregate error? And if we do, how are we going to go through and do that in a way that makes some sense? Talked about a priori comparisons. Again, these are you calling your shots, right? A priori comparisons are generally 2, 3, 4 maybe tests that you're expecting on the front end. And traditionally, and by convention, what we would do is just run these comparisons at per comparison error rates, right? You've called your shot, so you're getting some credit for, before you even collect your data, saying these are the things that I want to test, right? But other thing that happens is someone say, oh, I've got 20 a priori comparisons. Well, probably going to have to adjust for something along those lines, right? So again, traditionally, if we've got a priori hypotheses, contrast that we expect on the front end, you can get away with looking at those assuming you've got a small set, looking at those at per comparison error rates, but sometimes people, even if I've got 2 or 3 tests, just to be a little bit more stringent, we'll institute a Bonferroni or a Dunn-Siddick correction there, okay? And with our Bonferroni and our Dunn-Siddick correction, what are we doing with this? Someone remember? It's really simple. But what are we doing with our Bonferroni, Sam?
We're just making it more stringent.
Yeah. And what do we make more stringent? The alpha level. Okay. Sometimes people get turned around and start doing weird stuff with their test statistics. Don't, or their critical values. Like don't do that, right? What we're just doing is we're just calculating a p-value like we always do. But what determines whether or not we claim statistical significance for something is whether or not that p-value falls at or below our corrected alpha level for Bonferroni and Dunn-Siddick, right? Bonferroni is pretty simple. Let's say I'm comparing, I've got 3 tests and I'm going to institute a Bonferroni correction for that, right? I would take 0.05, divide that by 3, and my per comparison error rate then is going to be 0.017, right? And so any p-value that I get that's 0.017 or less, I'm gonna say that that's statistically significant, right? But if it's 0.02, then it hasn't met my more stringent threshold for bond firming, okay? Same thing with Duncitic. Duncitic is a little more lenient. It's actually pretty close. Duncitic is more exact in terms of correction here. But what we're doing is we're taking 1 minus our alpha level and taking that, that difference to 1 over the number of comparisons that we're going to make, right? So if I've got, again, 3 tests, but let's say I've got 4 tests. I'm going to take 1, 1 minus 0.05. Okay, it gives me 0.95, and then I'm going to take 0.95 to 1 over 4, that's 0.25, okay? And then I'm going to say I'm going to end up taking 1 minus 0.987258, whatever that is there. And so I'm going to get, again, a Duncitic correction for 4 tests here of 0.012, 0.013. Okay. So again, just remember that all we're doing with the bond firming and Duncitic is we're just adjusting our alpha, calculating p-values just like we normally would. We're not screwing around with anything else. So don't get confused. It's a little bit different than like our TB test. It's along those lines. Okay. People comfortable with this? All right. And then our post hoc comparisons, right? Post hoc comparisons is what happens when we don't have any something truly exploratory, right? And we want to go through. And the thing is, remember with this is post hoc stuff. As soon as I look at the means, right, and I say, oh well, turns out I remember now. I just really wanted to test these 2, right? Well, you're cherry picking the means that are as far as different apart from one another as possible, right? Or you're looking at something that looks cool. Once you've looked at the means from a conceptual, theoretical, philosophical standpoint, essentially you've run all those comparisons here in your head already, right? So what we're going to do is we're going to go through and correct for all those comparisons that you ran in your head, even if you're not doing them all on cranking out the statistics on all of those. So again, we can go through and do this, and this can be an appropriate way to approach things if you've got a truly exploratory type of situation. But particularly in these mixed designs where you've got a between subjects factor, within subjects factor, the number of different means that you can compare starts to get really huge, right? And so wanting to stay away from this to the greatest extent possible, right? And so, and you get pushback on this, right? Because people say, when you run these designs, people say, well, why don't you test this and this, and why don't we look at this and that? You want to go through and make sure, sort of ask yourself, does that make sense? Is this relevant to my design? And does this tell me anything meaningful within sort of what I'm trying to do, right? What I'll do in my study, in my sort of project, is I'll give you all the means of standard deviations. If there's something that interests you, go nuts, right? It's a free country, look whatever you want to, right? But for my study, what we've got going on, this is the important stuff, right? So I'm not just going to go through and look at 70 different thousand things just to do it, right? And so again, wanting to go through and approach this with a game plan. You've got a set of a priori hypotheses and maybe another kind of side set of exploratory analyses that you're wanting to go in. You just want to make sure that you've got a good way of going through, because again, it can be, you can go make yourself nuts testing all possible comparisons across all possible repeated measures and all possible groups, and then you've got 50,000 things that popped up positive because you ran 50,000 tests, and now you got to talk about them, right? That's the thing. If you find differences, you're obligated to account for them somehow, and sometimes the differences we find don't really make any sense in with respect to our theory and sort of what we were thinking. So want to be very careful and planful as you approach this stuff. Okay. Questions about this? All right. So follow-up test with our ordered means, right? If we've got, and again, we're talking about here our one-way design or one-way repeated measure ANOVA. A lot of times what's most interesting is there are different time points, right? If the order of those assessments start to be important, overall pattern or trajectory of what's going on is kind of an interesting thing with our ordered means, right? So example, excuse me, so in our VDI study, right, whether or not we've got lower symptoms at 2 weeks versus 3 weeks, right? If we go back, if you take a look at that, your handout on your ordered means, you take a look at that graph, right? Whether or not someone's different at 2 weeks and 4 weeks, who cares, right? That's not relevant probably, unless there's something important that went on between 2 and 4 weeks in terms of treatment or something, maybe. But in general, I mean, I can test those two things, but why, right? Unless there's a good reason to do it. Probably I'm more interested in the overall trajectory of these responses, right? And so what we can do is we can run a trend analysis, right? And our trend analysis is going to go ahead and give us a test of the shape of our means across our different repeated measures. Now this is different. It's not a trajectory measure. It's not looking at change. It's just looking at differences, patterns of differences across your repeated assessments. Okay, and the trend analyses, the results that you're going to get are going to be influenced by how different those means are and the order in the means at which the means fall out, right? So for our VDI example, trend analysis makes sense, right? What I can see is I can look at, is there a linear trend or a linear reduction in these means over time, right? Or is there some other type of change that makes some sense, right? If we go back to our unordered means, our vignette ratings, I don't know, maybe I find a trend, but I can just scramble those, the order of those around up, and then I'm going to get a different trend. None of that makes any sense, right? SPSS will give it to me, but I should know enough not to interpret it because it's not going to be meaningful, right? So when we're running our trend analyses, the types of stuff that we do, linear trends and maybe quadratic trends are going to be the most common, okay? When we start to get into higher order polynomials, so this is a linear trend. This is going to be a quadratic, or sort of the opposite, or excuse me, yeah, a quadratic. But then I start getting into cubic functions and fourth order polynomials. Maybe you've got some phenomenon that's going to follow that type of pattern, but I don't know, right? I mean, nothing off the top of my head would be something that I would expect to follow a cubic or a fourth order polynomial, and then the more bumps you add, the higher order polynomial you get, right? And so, again, SPSS will give these to you. Doesn't mean they mean anything, right? And they might show up as significant, but unless you've got a good theoretical reason to expect a fifth order polynomial, I wouldn't put too much emphasis or stock into that, okay? So, also remember, note that your trend is going to be influenced by the number of repeated measures. SPSS will give you a linear trend with 2 repeated assessments, a quadratic with 3, a fourth order, or a cubic with 4. Problem is with the 2 data points, a straight line fits perfectly, right? And so that might not be terribly meaningful. But depending on the number of assessment points that you have, you'll start to see SPSS lining out a whole number of different higher order polynomials. Again, that's a distraction. Don't pay attention to that unless you have a strong reason to expect some sort of cubic function where things go up and then they go down and then they go back up again. Okay. Questions about trend analysis? All right. Trend analyses, computationally, these are, we could calculate these by hand using the same procedure that we would use with planned contrasts. All we're doing is we're just weighting different means a little bit differently, okay? It's just easier to run these in statistical software. I mean, I could show you how to do them by hand, but that's starting to get, you don't have time to go through and do that, right? So we'll let SPSS cover this for us, but know that in terms of interpretation of these things, these types of follow-up tests usually are going to work better if you've got equally spaced stuff, right? So in our BDI example, where we've got a baseline measure, and then every 2 weeks, right, we're going through and evaluating people. So this is a nice thing. This falls nicely into this trend analysis. But let's say that I had a different treatment outcome study where I had baseline, post-treatment that was like 12 weeks later, and then I had a 3-month follow-up. It's going to be a lot longer out, and then a 1-year follow-up. I probably wouldn't want to look at that in a trend analysis, because trend analysis is assuming that all of those are going to be equally spaced, and it's going to start to get funky with stuff. Yeah.
Use a trend analysis as something that follows more of a normal curve. Does that make sense? Like, yeah, so not, it doesn't go back up like a.
Yep, that's going to be a quadratic.
Okay,
Right?
quadratic.
So your quadratic function, I mean,
Back down.
a quadratic is
Yeah.
a U shape, right? But if we just catch it right here, then it's just got a curvilinear shape to it, right? And so, again, you had something that was a parabolic like that. You could test that with the trend analyses. It's just kind of depending on what section you catch on that, right? So sometimes, like I've run growth models where looking at a quadratic trend for treatment, where you've got something like that, right? And that's not necessarily a quadratic perfectly, because a quadratic is going to start coming back up once it hits its minimum. So there's some other ways that I could probably do that would capture it better, but that quadratic term is catching the acceleration or the deceleration of change over time. Now this was not a trend. At the end of the day, with these repeated measures ANOVA designs, we're just looking at mean levels, right? So we're not specifying a growth function or anything like that, like we would be in like a growth analysis or an HLM or something along those lines. We're just looking at patterns of means. But we can kind of start to say, oh, this pattern of means is following a quadratic function where we're going down and then coming back up, or if it's a negative where things are going up and then they're coming back down. Other questions about trend analysis? Okay. So let's look real quick at, and pull up your ordered mean. So this is our BDI worksheet here. Gone through, we went through and took a look at stuff, right? We said, okay, here's our, make sure we've got everything loaded in correctly. If we go through and we're taking a look at our descriptive statistics, we can just see, just eyeballing the means, right, that we're seeing reductions in depression symptoms over time, right? We've got the same number of people at each time point because it's our repeat measures design. Same group of 388 people that we're following along. I would also take a look at your standard deviations, right? It looks like your variability is getting smaller as people are continuing through time. So a lot of variability where people are coming in, but as people progress through treatment, this is getting their variability. This looks like it's starting to get trending smaller. Multivariate tests, we're ignoring. Test of sphericity, we see that we've got a violation of sphericity, but we're just assuming that anyway, so we're not worried about it too much. We take a look at our test of within subjects effects, and we see that, yes, our analysis is suggesting that there's differences in average BDI score within our sample across different assessment points, right? And if we go down through and we take a look at our mean, our mean graph here, we see that it's very clearly and systematically reducing over the course of baseline 2 weeks, 4 weeks, and 6 weeks. Okay, everybody with me on that? So what we might want to do, because we do have ordered means, is we might want to go through and take a look at our trend analyses. This tested within subjects contrasts, this is our trend analysis, okay? And so if we go through and we take a look, okay, we'll see that we've got a significant linear trend, meaning that the pattern of means over the course of repeated assessments it's following a significant linear trend, right? And if we look at sort of what's going on, we're seeing linear reductions in symptoms over the course of repeated measures, right? So what we could do is we could run our trend analysis. We could say, looking at our omnibus test says we've got a within subject effective assessment, suggesting that there are differences in mean level of BDI over the course of intervention, and then we follow it up and we take a look at our trend analyses, and we have evidence of a significant linear trend here, okay? Suggesting that these the pattern of mean scores are reducing, coming down in a linear fashion over the course of intervention. Okay? I can also take a look, and I've got a significant quadratic, right? And this is kind of interesting. Quadratic is saying that it's not specifically linear, that it looks like there's some bend in there, right? And so this is actually not inconsistent with what we see in treatment outcomes, right? We often see a rapid reduction early on in treatment, and then as people kind of get close to as low as they're going to get, things start to go, sort of gains start to decrease, right? So we've got kind of this so it's not just a straight like this, right? It's kind of got a bend in it, right? And so what we might do is we might make an interpretation and say we also have evidence of a quadratic trend, right? Suggesting that the reduction in average BDI score over the course of intervention isn't exactly linear. It looks like there's a curvilinear piece to this, right? And then you can go through and talk about sort of what exactly is going on based on the mean values. Okay? But then you've got a cubic as well. Okay? Cubic function looks like this. Does that make sense, given what we've seen here? I don't know. I don't know what that cubic function is doing, right? If we take a look at our effect sizes, right? Our linear trend is accounting, that's a huge effect. We've got a huge linear change here. And then we've got a pretty decent quadratic effect. By the time we get down to the cubic, that's not picking up much, right? Other thing to remember is we got 388 people in a repeated measures ANOVA design, so we're going to be hugely, hugely powerful here, right? So what I would do, I would probably just ignore this cubic because it's statistically significant, but I don't know what it means. It doesn't make any sense or I guess we could invert this. Right? So we get people getting better and then they get worse and then they come back down. I don't know what's going on with this, right? So I'm not sure why this cubic popped up. It did, but just because something's significant doesn't mean, in an SPSS output, doesn't mean you have to interpret it, because I don't know what I would do with that. Okay. So again, with our trend analyses, we're just using this to go through and say, okay, what we've got is we've got, looks like on average, or across repeated assessments, our means are changing in some way within individuals. In my trend analyses, I've got a strong linear trend with reduced levels of BDI, or reduced BDI scores over time. We're also picking up a cubic, a quadratic component, looking that it's like there's some bit of curvilinearity to this, and then I just kind of leave it at that, right? And here, this might be a perfectly reasonable way to describe this, right? Do we need to go through and test whether or not we see reductions, significant reductions from baseline to 2 weeks? No. right? I mean, it's gonna be huge. I mean, I can run an effect, or a t-test on there if you want me to, but it's not gonna be meaningful, because I can just look at it and knowing the size of the sample and the magnitude of that reduction, I know it's gonna be significant. I can test whether or not people are different at week 2 and week 6. But again, that doesn't seem like a reasonable thing to spend my time on, right? So wanting to go through and think about what are we gonna do with these? What's our best approach to providing some sort of meaningful interpretation of what's going on? Yeah?
Could you give that justification in paper, an analysis like this, like based on the trend factors?
Yeah, I mean, I would just go through and say, in your analytic plan, say, this is what we're gonna do. These are the contrasts that we're gonna run. This is what we're gonna happen. And then you might get a review that says, well, why don't you do, so how many comparisons could you make in this set of scores? Remember, in this case, it's gonna be the number of means times the number of means minus 1 over 2, right? So we got 4 means, 4 times 3 is 12, over 2 is 6. 6 different means. So 6 unique pairwise comparisons that could be made in that. Do we need 6 pairwise comparisons to tell us what's going on with here? No. What I would do is I would provide mean standard deviation, let people go through and run their own stuff if they want to, right? Say, this is what we're doing, this is why we're doing it, and so as not to clutter up paper. Questions about our trend analyses, what's going on with this? Okay. So what I might do here, and what I did with this is, so maybe what I want to do is, okay, I've got a linear trend, but important within this, I want to capture the magnitude of the difference between reduction. So what is my effect size, right, for pre and post treatment? How much of a reduction am I getting in these data, right? And so what I might do, if I wanted to get a measure of effect for reductions from pre to post treatment, which could be important, right? I don't need to run a statistical test on that because I already know it's going to be significant, right? If I compare baseline to post treatment, that's going to be huge. But what I might want to do is I might want to quantify this effect. That starts to become relevant, right? Think about how, what's the effect size associated, pre-post effect size associated with this treatment. Seems reasonable, right? So what could I do? What do you think, Katie? What's that? So what, I want to get a measure of effect size. How might I go about that? Robots are coming for us. Anybody have thoughts? How might we approach this? Because I want to know, fine, I've got a linear reduction. I've got my ANOVA test tells me that I have significant change or significant differences in means over time. What might I do? How might I want to go about quantifying the magnitude of this effect? What do you think, Sam? What could I do? Yeah. And so what would be my options for calculating that effect size for pre and post? Perfect, yeah. Glasses delta. I could run glasses delta on that, right? And what's unique about glasses delta? Or what am I doing? What makes glasses delta? The standardizer, remember my standardizer is going to be baseline variability, right? So I'm going to use standard deviation of scores here, right? In terms of standardizing my effect. What else could I do? this, Alex?
Paired sample test.
I could do a paired sample test. Probably don't need to do a paired sample test because I already know what that's going to turn up. But what could I use from a paired sample test if I wanted to calculate effect? What are my other options in terms of, and I mean, this is going back a bit from last semester. So I could use, the question with my effect size is always, what am I using as my standardizer, right? The difference is easy. That's pre-post, right? Nothing controversial there. But I have some options in terms of what I want to do in terms of quantifying the magnitude of this effect. So what I could do is I could calculate a confidence interval around the difference, right? I could go through and say, all right, average within this sample, this is the number of points reductions in VDI that I get, right? And this is a confidence interval around that. That's kind of a meaningful thing, right? Particularly if this is a treatment outcome study, because I run my study, Ken is like, well, I'm working with a group of depressed people. How much can I expect people going through this treatment in terms of improvement? How much are they going to improve? Well, I can say, well, based on this, we see a 20-point reduction on average based on our data. That could be anywhere from, we expect anywhere from this to be, in terms of raw points on this outcome measure, the number of points that we would get with a replication, right? And that's kind of meaningful, right, within this setting, is because it's giving me the magnitude of reductions in sort of this, in points that we can expect over the course of intervention. So that's something that might be worth looking at, right? I could also run different standardized measures of effect. I could run a glasses delta. I could go through and say, we see a 1.5 point standard deviation, a standard deviation and a half reduction in scores from pre to post treatment, right? Based on variability at baseline. That's something we can do, right? We could do something that looks like kind of a Hedges G, right? Where we would take the average variance at baseline and post-treatment because normally we would pool it, but why don't we need to worry about pooling it? Same number of people, right? So we don't have to pool anything. We can just take the variance pre and base and the variance of post. We just take the average of those and then take the square root of that average variance to get a kind of an average standard deviation. We can do that, right? Or we could go through and look at standardize our difference in terms of standard deviation of the difference score. That's what we get with our paired sample t-test, right? Now, downside to paired sample t-test is the standard deviation of our change from time 1 and time 2. The standard deviation of our difference score is often quite a bit smaller than like standard deviation at baseline and things along those lines. We have some concerns that may make our effect size look too big, right? So if everybody's all over the place, right, we've got a range that the scores to start are anywhere from 10 to 100, right? And at the end, everybody is different from 0 to 90, right? So a lot of variability at pre and post. But if everybody changes by about the exact same, standard deviation of the difference scores are going to be much smaller, right? And so we want to make sure that we're not inflating our effect size by using the standard deviation of the difference score as our standardizer. What's the one thing that we can do if we do that? What's the benefit? We can calculate a confidence interval around our effect size if we're using that as our standardizer. Remember, how do we get the upper and lower limits of our for our effect size? We got go for it, Katie. The non-centrality parameter, right? And the non-centrality parameter comes directly from our statistical test. So whatever we're using as the standardizer for our point estimate has to be the same variance estimate that went into the calculation of the standard error for my statistical test. If we're using the standard deviation of difference scores, my standardizer, then everything lines up and I'm good to go, right? But if I don't, if I like calculate a Glasses delta and then try and calculate a confidence interval using non-centrality parameters for my paired sample t-test, I'm going to get a confidence interval and my point estimate's going to be over here, and then that's not going to make any sense, right? So So these are the things that we need to go through and think about. So for this example, what I might do, even though I don't need to run the t-test because I already know that it's going to be different, what I might do though is run one anyway, just because this t-test, and I'm not interested in the p-value. What I'm interested in is going to be the values that I get off of this that are going to be helpful for me, right? So what I can do is I can go through and say, okay, well, I ran my between subjects test, or my paired sample test. So I'm comparing, in this t-test, I'm looking at the difference from pre to post, right? But what I can do right here, my output in SPSS gives me the mean difference from pre to post, and it also gives me the standard, or the a 95% confidence interval around that mean difference, right? And that's kind of useful, right? So I can say here that individuals in this study demonstrated an average reduction of nearly 18 points on the VDI, and we would expect reasonable upper and lower bound reductions in the population based on these data to be a reduction of anywhere from about 16.5 to about 19 points. Right? We've got a pretty tight interval on this. Why is that? We got 388 people in there, right? We've got a big sample size, so it makes that confidence interval pretty small, right? So this in and of itself is nice. I don't have to worry about calculating this because I can just go through and, I'm running my statistical test, but SPSS is just going to give it to me anyway, right? So this, in the context of this, so those of you who aren't clinical people, maybe means less, but for us, we use this measure a whole lot, right? If you say close to an 18-point reduction on the VDI, I'm like, that's pretty decent, that's pretty good, right? That's something that means something, and so I can express the magnitude of the change here just based on the difference in the confidence interval around that difference score. That could be something that would be meaningful, right? Other thing I can do is I can go through and I can calculate a glasses delta, right? And that's a nice effect size because what we're doing is we're looking at the change from pre to post relative to variability at baseline, right? So if I want to calculate glasses delta, I might go 17.791. And again, that's nice. I mean, I can calculate that by hand, looking at the mean at the start and the mean at the end, but SPSS just gives it to me, so that's nice, right? Over, and again, if you take a look up here, we see the standard deviation at baseline is 9.551. So that's going to give me glasses delta of 1.40. Okay. That's pretty good, right? I've got a 1.4 standard deviation decrease in BDI score from pre to post and standardized using a standardizer based on variability at baseline. So that's kind of nice. I could also calculate.
Do you not use the 12 for the intake for baseline?
Oh, whoops. Yep, you're right.
Sam caught that. So.
Okay, thank you. Nice work, Sam.
Yeah, there it does. Yeah, because I need to, I got different values too.
Okay, there we go. Thank you, Lauren. Shame on you, Sam, for being to not correct my mistakes. Okay, so we've got glasses delta there. Other thing we could do is we could calculate DAV, right? And again, this is just kind of using, this is kind of like a Hedges G, except we don't have to go through the whole rigmarole of pooling things, right? So we can go through and we could say, if I take my standard deviation and I square that to get my variance, right? I'm going to end up with my average variance is going to be 91.222 plus 160.8 985 over 2. Okay, so I'm just taking my SPSS gave me standard deviations. I'm just creating variances with those. I get an average variance of 126.103, right? And then I can take my average standard deviation, take the square root of that, and it gives me 11.230. Okay. Remember, we can't just take the average of the standard deviation. The average standard deviation isn't going to be equal to the square root of the average variances. Okay. And so what we're going to do here is we can go 17.791, right, over 11.230, and that's going to give me 1.58. Or what I could do is I could go through and say, all right, I want to, because what I want to do is I want to be able to, I mean, I got a big sample. I want to go through and calculate a confidence interval around my effect size, right? And if I want to calculate a confidence interval around my repeated measures effect, I have to use standardize using the standard deviation of the difference score, right? So I can go 17.791 over, if I look at my table, standard deviation of the difference score here is 12.668. And that's going to give me 1.4 again. Okay? But what I can then do is I can go through and calculate a confidence interval around that. It's going to be end up 1.26, 1.54. Okay. And so again, what we would do if you go back into your 50-60 notes, right? What we would do is we just take the t-test and the degrees of freedom from our paired sample test, plug that into our non-centrality parameter, get our upper and lower bounds of our non-centrality parameter, convert that back into the upper and lower bounds of our effect size here. So any of those are things that we could do within the context of this study, because we've got ordered means, right? And it doesn't make sense to look at all possible comparisons across these repeated measures, right? But what we can do is we can say, okay, what's our strategy? How are we going to go through and take a look at this? Well, if I'm looking at this, my trend analysis makes some sense. I've got a linear trend, and sort of that significant quadratic trend suggests there's some curvilinearity to that, which makes some sense. We often see that people, as treatment starts to continue, their gains start to taper off a little bit, right? So that makes some sense given the phenomenon that I'm thinking about. But then I might also want to go through and provide some index of the magnitude to change from pre to post treatment, okay? And I don't need to necessarily run a paired sample test. I could and say it's significant, and maybe the reviewer wants me to, just because they want to look at a p-value that says p less than 0.001. I can eyeball it and know that, particularly with 388 people, that that's not necessary, but fine, I'll do it if you want me to. But what I can do is then run through, and if I just run this t-test in SPSS, what's nice is it goes through and it gives me all the stuff that I need to go through and make a decision on what type of effect am I going to report and what's going to be most meaningful, right? And here we could talk about this in terms of raw reduction of points, which is kind of meaningful in this situation, right? Say, this is the confidence interval, so if someone else were to go through and run this same treatment with another group of people who were hospitalized for psychological difficulties, we can say, well, we would expect you to have about a 17-point decrease over the course of a 6-week treatment with sort of the upper and lower bounds of that being about this much reduction. That's kind of meaningful. Or we could standardize it, right? And here, you know, we're always our worry with our using the standard deviation of the difference score is that it's going to be inflated. Here it actually doesn't look like that's a big issue. And so I might choose this just because I've got a big sample. Confidence interval around my effect size is going to be kind of small, so I can provide a confidence interval around the magnitude of my effect. Or if I want something that's more interpretable, maybe just go with a Glass's delta. Just kind of depends on how I want to report this. Okay. So people sort of get a sense for how we might go through and start to tease apart and run follow-up tests on this with this sample with ordered means. Any questions on any of this? Okay, cool. Unordered means starts to get a little more tricky, okay? We have to have, we have some guidance with our ordered means because kind of got to do things a certain way. It doesn't make sense that, we have more guidance if the ordering of our means makes some sense, right? But if I have unordered means, right, like our second example where we just went through and we actually counterbalanced the order in which people were rating these different vignettes, right? And so the order of it doesn't matter. But, so what we want to do, if we've got a situation where no meaningful order to our means, or our repeated measure has a meaningful order, but it doesn't necessarily follow a polynomial function, right? So it's not, the order makes a difference. You can't just scramble things up, but it's not necessarily following anything that looks like a nice sort of mathematical curve, right? Then what we can do is we can go through and follow up with planned contrast or paired sample t-tests. Okay. Contrasts. Okay. Remember, the nice thing about contrasts is contrasts are allowing us to compare not just two different groups or two different means, but we can go through and look at sets of means. Okay. And what this does is it gives us a more flexible approach. We can test more specific hypotheses if we're allowed to combine different groups in a way that makes sense. This can be intimidating. Who's intimidated by planned contrast? I am sometimes, right? But it's just it's just a generalization of a t-test, right? So it's not anything that's different than what we would do with a t-test anyway. We're just kind of tweaking how we're setting things up, okay? So remember that with our contrast, what we need to first do is specify a linear combination of means. And what we're going to do is we're just going to choose, take the means that we're interested in comparing, and we're just going to assign a set of weights to those means, right? And so the value of my contrast here is going to be the sum of my weighted means. So again, if we set a weight of 1 to all of these means, then what we're going to get is just the sum of the means, right? If we went through assigned weights where it was 1 over however many means we had, we just get the mean of the group means, right? But what we can do is we can start playing around with this stuff is if the sum of our means is equal to 0, what we have is a linear contrast, okay? So I've got 3 means here. I've got x1, x2, and x3. And what I want to do is I'm going to assign a weight of 1 to x1, negative 1 to x2, and a weight of 0 to x3. What am I doing in this linear contrast step?
You are comparing 1 and 2 versus 3.
Okay. Close. Is 3, if I weight 3 with a 0, is 3 included in this contrast? No. So we're just going to we're going to compare 1. So with this set of weights, right? And if I have 1 and negative 1 and 0, I get 0, right? And if the sum of my weights across all my means equals 0, then I have a linear contrast. Okay. And so again, what this is going to do is it's just going to compare mean 1 to mean 2. Mean 3 is not going to be included, right? And so again, if I go weight 1 to mean 1, negative 1 to mean 2, plus 0 to mean 3, we're just getting a difference between group 1 and 2 here. If we go through and we set weights 1/2, 1/2, and negative 1, Sam, what are we doing in this contrast? The combination, we're looking at the combination of means 1 and 2 and comparing that against mean 3, right? And again, if we add 1/2, 1/2, and negative 1, the sum of those weights equals 0. We've just got another linear contrast. So again, 1/2 times x, it's just the average of means 1 and 2 versus means 3, right? We're good to go. And so what's nice about these contrasts, and these are underused at least in clinical stuff. This used to be the bread and butter of experimental designs, and we don't use them a whole lot anymore. But what we can start doing is if we got, all right, I think these two groups are going to be kind of comparable. I want to compare them to these, this other group. We can start to be very flexible in how we go through and start to tease out more interesting and specific types of tests than looking at. So I've got one experimental group and 3 control groups, right? Instead of doing experimental against control 1, experimental group control 2, experimental against control 3. If I don't think those control groups are all going to differ, I can just take experimental against the combination of control groups. That's a much more efficient way to go through and do this with 1 test instead of 3. Okay? And if I don't think that there's going to be a meaningful difference across these different controls, cool, let's just run it that way. So again, sometimes what can be difficult is identifying what our coefficients for our contrasts are going to be. It's actually pretty simple in terms of how we set this up. What we're going to do, identify the sets of treatments to be compared. Right? So I've got 4 different means. Maybe I only want to look at 3, right? Identify how many means are going to be compared in this contrast. Then I'm going to assign weights as the reciprocal of the number of treatments in the set, right? So I've got 4 means. I'm only going to look at 3. I'm going to compare this first one to these other 2, right? What I'm going to do is my weight for the one group that has 1 mean in it is just my weight's going to be 1. Weight for my other group, there's 2 means in there. My weight's going to be 1/2, right? And then we just assign coefficients in one of the groups to be negative. Generally, what we'll do is we'll make assign the negative weight to the negative sign to the weights of the group or the conditions that we think are going to be smaller, right? And what's nice is then that just means if we take the mean or the groups that we think are going to have higher means against means that we think are going to be lower, and the ones that we think are going to be lower, we assign a negative contrast to, then it's just everything turns out sort of the right direction, right? So the value of our contrast, the sign actually means something. So if it's positive, it means that the group with the higher mean is higher, and if not, I mean, it doesn't make any difference from a mathematical standpoint. This is more about interpretation. Okay? So let's say I've got 5 means, right? And what I want to do is I want to compare the combination of the first 2 means against the combination of the last 3 means. So here are my means. I'm going to assign weights as the reciprocal of the number of means in each group, right? So I've got 1/2, 1/2, and then for these other 3, -1/3, -1, -1/3. Okay. And in this case, Lauren, who am I expecting to have the higher values? What group am I expecting to have, or set am I expecting to have the higher values on? Yeah, right. I'm expecting the combination of these means to be larger than the combination of those means, right? And in that way, my value, my contrast is going to be positive, consistent with how I've kind of set this up. And so what I do, the sum of my weighted means is going to be 1/2 times the sum of x1, x2 minus 1/3 times the sum of x3, 4, and 5. And so this is going to be the value of my contrast here. Okay. Also, we have a situation if we formed a standard set. Okay. If we sum up the values of all of our weights, and the sum of our weights is equal to 2, we've got a standard set. And what's nice is when we're calculating the value of our contrast, the value of our contrast literally represents in the units of our measure sort of the difference between this group, combination of group, and that combination of group, right? I could set these weights here. I could set that to 3 and 3, and that to -2, -2, -2. I'm still going to get the same statistical test. I'm still going to get the same p-value. But now the difference between my one group and my other group, it's not going to be in the same units that the original variables are. And so what's nice if we're using it, if we set our weights to conform to a standard set, what's nice is that we can then just use that value of our contrast in our effect sizes and all that type of stuff, right? I don't have to recalculate anything. Okay. So, but note that if we have largely different sample sizes across our groups, this starts to complicate things. Again, we're assuming a balanced design. Now, in our one-way analyses, we don't have to worry about this, right? We, by definition, have the same number of people in each cell. But as we start to work the in-between subjects factors, we can start to get differences, and that's where we want to, things start to get a little bit complicated. Okay. People sort of, and so this is all refresher. This is just hijack stuff from 50, 60, but people kind of remembering sort of what we're doing with these. Okay. So linear contrast for our repeated measures ANOVA, all right? This formula is going to be a little bit different than some of the stuff that we did before, so you got to make sure that you're using the right formula. Value of our contrast is just the sum of our weighted means, right? What we just calculated before. And then our t-test is going to be the value of our contrast over the square root of the sum of our squared weights times the mean squared error that we pull from our ANOVA table over the number of people that we have in our design. Okay. And so then what we do is we evaluate our test statistic against a critical D with degrees of freedom pulled from our overall ANOVA table, specifically from our within subjects tests. So pretty simple. In order to go through, we'll go through and work through an example with our unordered means, just so you can kind of get a sense for what's going on here. But people have a question about how we set up these contrasts. Okay. Other thing we can do for pairwise comparison, we just fall back on paired sample t-tests. Okay. Our concern is just run a bunch of paired sample t-tests, all possible paired sample t-tests, and that can get real. We can get a whole lot of those real fast. We want to be careful with that, but what we then can do is then start to, we have a small set of planned comparisons using von Fermi, Dunn-Civic, something like that to manage some of our family-wise error. Okay, so something to think about. Our traditional approach to contrast and follow-up tests and things along those lines, having this pull terms from our repeated measures ANOVA, okay? And so what we do is this makes for more powerful tests, right? Because our critical values that we're comparing against are based on degrees of freedom from the whole model, as opposed to just degrees of freedom for the specific groups that we're testing, right? And so definitely a more powerful test, but again, we start to worry about violations of homogeneity, discrepancy in cell sizes if we have between subjects factors and things along those lines. As we start to get increasingly complicated designs, some of this starts, what ends up happening is we start to become concerned about whether our model falls into the very specific assumptions of some of these contrasts. So again, we can use these if we've got specific hypotheses that we're looking to test, and we can use these if we've gone through and made sure that most of our assumptions are reasonably met so that we can have confidence in our results. But remember that, and this is based on Howell, right? And Howell will talk about, you know, if we've got discrepancies in cell sizes, if we've got people kind of all over the place, there's going to be an issue with when we get our between subject factor in there, or if we've got clear violations of homoskedasticity, or not homoskedasticity, homogeneity of variance, right? These are some things that we can start to go through and say, maybe I could do this, but I'm sort of worried about it, particularly if you're looking at pairwise stuff. If you got big violations and other concerns about stuff, sometimes it's better just fall back on paired sample t-tests as long as you're just concerned about pairwise tests. Now, if you're wanting to look at combinations, then we're back into contrast. Just have to know that do I have concerns about reasonable interpretation of these effects, given that I've got some violations in my design? Questions on this? Okay, so let's go through and pull up our unordered means. So here, again, what we've got, just as a reminder, we went through, had people read different vignettes and then report whether or not they would be willing or unwilling to maintain friendships with the individuals, specified hypothetical individuals in these scenarios. And so what we did is we went through and took a look at our screening. Again, our F max wasn't terrible. I mean, it was 3.1, but it looks like our variability across our individual means isn't terrible. We obviously, it's a one-way within subject design, so we've got all the same number of people. We went down through and we found that within this design, we do have evidence that there are differences in the mean friendship rating across repeated assessments. But what we want to do now is we want to go through and get a sense for where these effects coming from, right? Alex, what was the thing that so if we look at this marginal means graph, it looks like we've got huge differences across these. What was our caveat to interpreting that?
It was 0.6 difference.
Yeah, right. SPSS scaled that and blew it up, so like did the super zoom. But there's really very, very subtle differences between these means, right? And so what we want to do is we want to come up with some sort of way to go through and tease some of this stuff apart. Now, just to run through an example, let's say at the start of this, the vignettes, remember that 4 of these vignettes involved exposures that were traditionally traumatic in nature, and 4 of them didn't, right? And so maybe our hypothesis is, and what we want to take a look at, is want to see whether or not people are more likely to maintain friendship with people who are exposed to traumatic stressors versus non-traumatic stressors. Okay, and remember when we set this design up, right, we took the 4 different scenarios that were traditionally trauma-related. So car accidents, combat, sexual assault, and disaster, we layered those first. And then we layered in infidelity, illness, sort of job relocation, and financial ruin, right? And said, hey, are you willing to, so this is happening to this person, would you be willing to maintain friendship? And maybe our question is are people more willing to maintain friendship, provide support for people who've been exposed to trauma-related stuff versus non-trauma stuff, which seems reasonable, right? We'll pretend that this was one of the things we wanted to take a look at in this design, okay? So how many trauma-related scenarios do we have? 7? How many of, well, how many are traditional trauma? Oh, yeah. Oh, okay. So we got 4 of these, right? So we've got 4 of these that are trauma-related and 4 of them that aren't, okay? So what we want to do is we could run a contrast to look at this, right? And so first thing we need to do is figure out what our weights are going to be here. Katie, any thoughts on what our weights are going to be for this contrast?
Here's 4 negative 1.4 that are
Perfect, right? So what we're going to do is we're going to weight each one of these with 1/4. And my hypothesis is that people are more willing to provide support to people who have been exposed to trauma than the people who are exposed to non-trauma stressors. And so what I'm going to do is I'm going to actually flip those weights around. So what I'm going to do is I'm going to say value of my contrast is going to be 1/4 times, okay? And this is where we got to go back through, and we've got our mean values if you go back through and take a look at your descriptive statistics on your handout, right? And so what we're going to do is we're going to say value of my contrast is going to be 1/4 times 7.645 plus 7.338 plus 7.645 plus 7.636, okay? That's going to capture all my people who are, or this is going to capture ratings for trauma-related vignettes, okay? And then I'm going to say, I'm going to subtract 1/4 times 7.152 plus 7.615 plus 7.134 plus 7.359. Yeah. Okay. So I've got a lot of means that I'm comparing here, right? And with 8 different means, how many possible comparisons could we have? Whatever 56 divided by 2 is, okay? Then I'm going to have 8 times 7, right? Because we've got n times n minus 1. 8 times 7 is 56 divided by 2. What is that? What is it?
56 divided by 2?
Yeah, 32. I got 32 possible pairwise comparisons that I could make in there. That's a lot. No, that's not right. That's
28.
28, there we go. I'm too trusting of a person. There's 28 possible pairwise comparisons that could be made in this graph. That's ridiculous, right? We don't need to do that. So what we're going to do is we're going to run this contrast and say, okay, do we see that on average people are rating more willingness to provide friendship to people who are exposed to trauma-related stuff or non-trauma-related stuff? Okay. And so the value of my contrast in this scenario is going to be 7.571 minus 7.315. Any reactions to that? From a just a practical standpoint, what is this contrast suggesting? Not a huge difference, right? This is a very, very small difference here, right? On average, people are kind of reporting the same thing. But if you think about what we're doing here, we're giving people a vignette and like, hey, would you help this hypothetical person out, right? It's kind of pulling for yeah, right? But so if we're able to detect differences in here, I mean, what we need is a really powerful design in order to detect differences. Fortunately, we've got a lot of people in the sample. We've got a repeated measures design that's really powerful. And so if we're going to get this is the type of design to be doing it in. Okay, so we end up with a value of our contrast 0.256. Okay, and so this is what's nice about. So literally, this is telling us the average difference in, or the difference in average rating for trauma versus non-trauma scenarios. Okay, and this is where that standard set starts to come in, because we could go through. I could make that the weights for this. I can make that 3 and the other one -3, or this 100 and that a -100. I can make it whatever I want, right? Because it's still going to sum up to 0. But what ends up happening if I have a standard set is this is now interpreted as the actual difference in average ratings across these 2 different sets, right? And so that's what's useful, because now I can just calculate this once, and then I can go through and start using this as for my effect size and things along those lines. Okay. So this is the value of my contrast. So when we're looking at my T statistic, right? I've got 0.256 over, okay, of my squared weights. Okay. So what I could do is I could go through and I could take, basically, how many weights do I have in this set? 8, right? And so what I would need to do technically, if I'm going to calculate this long form, I'm going to go 0.25 squared plus 2.5 squared plus 2.5 squared, all of those, right? And I could write that down, but that would be kind of a lot to write out. So I'm going to shorthand this. I'm just going to go 0.25 squared times 8. We've got 8 of those, okay? People see what I did there? I mean, the summation, it would be a long thing to write out all the way, okay? So we've got the sum of our squared weights times, what goes in here next? Mean squared error, right? And if we look at the mean squared error, and what I'm going to do here is I'm going to take the mean squared error from my greenhouse geyser correction, right? We probably shouldn't take sphericity assumed because we never assume sphericity. And so what I'm going to do is I'm going to pull the mean squared error from my greenhouse geyser, right? I'm going to say 0.766. And I'm going to take all of that over the number of people in my sample is 231. So my t-test is going to be 0.256 over, and if I work that out, it's going to be 0.041. It's going to give me a t-statistic of 6.29. People are getting. Now, is that t-statistic going to be statistically significant? Yeah, we know it's going to be, right? But the thing is, sometimes it's not always going to be that clear, right? And so remember that with this contrast, we're testing this against a test statistic with a critical value, with a t-critical, with how many degrees of freedom? What's that? Okay. Remember that we're, what's that? Okay. Remember that where did we get our mean squared error from? Pulled our mean squared error from our ANOVA table, right? And with the traditional approach to calculating these contrasts, what we would do is we would use the degrees of freedom that we pull from our ANOVA table as well. So we're actually testing this against a test statistic, a critical T with, we'll say, 1,177 degrees of freedom. Okay. So this is where we get huge amounts of power out of this, at least in terms of reducing. Now this is going to be significant if we use any degrees of freedom, right? But technically, if we look at the degrees of freedom that are associated with our mean squared error term that we use to calculate this, it's 1,177.905 is the greenhouse adjusted. So we'll just sort of round down because we don't want to claim more degrees of freedom than we have. It's kind of ridiculous at this level, but 1177 is what we were working with. And so technically, our critical value is 1.962. Right? So it's kind of gravy at this point, right? So we've got a clear statistically significant effect based on sort of our contrast. And this is really important, right? Talking about the difference that we saw between the average friendship rating for our trauma versus our non-trauma groups, it's really small, right? But with the way we set this up, right, we kind of grabbed a lot of people, right? But what we're having is we're, again, having people rate counterbalanced vignettes across a set of 8 of those vignettes. We were able to pull a lot of that stuff, a lot of the individual differences out. I don't know what type of sample I would have to get if I were having a different group of people with rating each one of these vignettes and run this as a between subjects test, but it would be a ton, right? So we're able with this design to pull out very subtle differences just based on the fact that we were using our repeated measures. Okay. So last thing we might want to do here is calculate an effect size. Okay. And so in this case, what I might want to do is go through and calculate a pooled estimate for all of the means or the cells that are included in my test. So if I go up and take a look at now these are my standard deviations, but we can go through and square these. Again, what's nice, if we're going to pool all of these, do we need to worry about our pooled estimate or our pooled formula? No, because we've got the same number of people in each one, right? So if I wanted to calculate my pooled variance, I can say variance pooled is going to be 0.770 squared plus 1.179 squared plus 0.850 squared plus 0.838 squared plus 1.351 squared plus 886 squared plus 1.266 squared plus 1.106 squared. We're going with a lot of means, right? Or a lot of different observations, so this is kind of a pain. But we take all of that divided by 8. That's nice, right? And we get up, end up with a pooled variance estimate of 1.105, which gives us a pooled standard deviation of 1.051. You see how I'm getting that? Cool. And then, all we need to do is calculate our effect size. We've already got value of our contrast, right? We use a standard set with this. And so we can just go through and pull this as the literal difference in points, right, in our metric that we're using between the combination of our ratings for our trauma versus non-trauma groups over our standard deviation, our pooled standard deviation that we calculated is going to be 1.051. Going to give me an effect size 0.244. So this can get kind of tricky, right? And you want to just have a good game plan for how you're going to go about pulling these apart. Now, is this the only way we could go through and pull that apart? Now, there's all sorts of different ways we can go through and do it, right? Our omnibus test says that these patterns of means, the pattern of means are different across repeated assessments. There's a lot of different ways that could be different, right? This doesn't capture them all. But if this was our primary hypothesis, this would be the thing that we would do. And then maybe if there were some exploratory stuff, we might want to do that and sort of layer in some stuff afterwards, right? But again, you drive yourself nuts looking at all possible comparisons between all possible things, right? And that's probably not going to be meaningful within this because it's going to be too much for me to go through and account for. So we want to go through and have, I mean, you can do it, then you got to talk about it, you got to defend it, probably ought to correct for 28 comparisons. That's going to be ridiculous, right? And so again, thinking about this in terms of if you're going to run it, you have to correct for it, or if you're going to look at all possible comparisons, you're correcting for tests that you don't have any interest in. That's not doing you any favors, right? Someone could say, well, why don't you look at this, that, or the other thing? Well, I could, but that wasn't the reason I did it, right? This is why I did it. This is why I was interested in it. Here are the mean standard deviations. If you're interested, go nuts. But this was the reason I ran the study in the first place. So again, using just a lot of the same principles from last semester, did this go through kind of make some sense and help out in terms of getting everything squared away? Okay, any questions? All right, cool. Let's take 10. We'll jump back in and start working through other stuff with you back. All right, friends. Last thing we want to go through and talk about with our one-way designs is how to go through and look at some post hoc stuff, all possible comparisons, some different things to keep in mind with this. Okay. So a couple of different things we can do. Okay. If we're not concerned about combinations of means, and I need to do this, and this is the updated. Pull down the updated one.
Yeah, I just downloaded it, but apparently I downloaded the wrong updated one. Sorry, I'll find it.
Okay. So part of this is changing my thinking about how to go through and tease this apart, give you guys some efficient means of going through and looking at stuff. If you've got a small number of repeated measures and you're truly agnostic on how this is going to go through, like completely exploratory, right? There are scenarios here where maybe looking at all possible pairwise comparisons might be something that you might want to do, okay? But just remember when you're doing this, that you're getting charged for every comparison that you make. And if there are comparisons in there that aren't interesting to you, you're still paying for them, okay? Now, again, in your one-way repeated measures ANOVA, okay, one thing that you could do in SPSS, what you could do is you could select options in your repeated measures window and click compare main effects. And then you can select procedure, you can ask for Fisher's least significant difference, Bonferroni, then SIDAC corrections. Okay. So to give you a sense of what that would look like in, let's say, here we go, analyze general linear model repeated measures, right? And here we've got 4 means. This is our ordered means. Just doing this quick to show you where this is at. We want to look at ADI intake, 2 weeks, 4 weeks, 6 weeks. Contrast is going to give us our polynomial plots. We want horizontal there. We add that. This is all stuff that we've done before. Post hoc, not going to give you any post hoc because there's no between group differences here. But if you go down, you hit options, right? And we say display means for factor 1. I want descriptives and estimates of effect size. Homogeneity variance tests, it's not going to give us because we don't have a twin subjects effect. But what you can do, we can hit compare main effects. Okay. If we hit compare main effects, and then we can choose whether or not we want least significant difference, Bonferroni, or Dunn-Siddick. Right? Let's leave it at least significant difference, continue, and hit OK. is all the output from, again, our ordered means that we'd seen before. But if we scroll down to the bottom, you'll see that now what SPSS is doing is it's giving us all of our pairwise comparisons. So if we take a look, we can see we're comparing baseline to 2 weeks, baseline to 4 weeks, baseline to 6 weeks, 2 weeks to baseline, 2 weeks to 3 weeks, 2 weeks to 4 weeks, so on and so forth, right? You get the sense, right? And what this is doing is, because I've just selected the least significant difference. With Fisher's LSD, is there any correction for multiple comparisons? Nope. Fisher's LSD doesn't provide any correction. This is just looking at these tests at per comparison error rates. And what SPSS is doing when we select this is it's just running paired sample t-tests for each one of these. Okay? So with Fisher's, if you go through and if you were to run a paired sample t-test, comparing baseline to time 2 or baseline to time 3, so on and so forth, and you look at your mean difference and your p-values, now these are all hugely significant, right? And then your confidence interval for your difference, it's going to be identical to if you were to have gone through and run a paired sample t-test for those time points. Okay. So this will give you very quickly, in your one-way ANOVA designs, this will give you a paired sample t-test for all possible comparisons. Now, it's not giving you an actual t-statistic, but if you take the difference divided by your standard error, that'll just give you your test statistic. It's not listing it out here, right? So you can get this very easily in SPSS, okay? Questions about this or what we did there? Now, the issue is, this is easy and fun to do. Problem is, there's no correction for this, right? And it's going to give you a lot of tests. It's going to give you all possible comparisons in your one-way design. Now, are all possible comparisons interpretable in your one-way repeated measure design? Yeah, right? You just got one group. I can compare any two individual repeated measures assessments if I want to, right? But it's going to give you a lot of stuff that's not necessarily useful, right? I don't know that I care whether or not there's a reliable difference between people's BDI scores at 2 weeks and 4 weeks. Maybe, again, if there was something that went in between that time, but maybe not, probably not, right? But it's still going to give you all of these, and it's not going to correct for any of that stuff, right? And so wanting to be aware of that, if I went through on that pull-down menu and I selected Bonferroni and Dunn-Sidek, it would run all those comparisons, but it's going to correct for, we have 4 means, 4 times 3, so we got 6 pairwise comparisons. It's going to Bonferroni correct for 6 pairwise comparisons, even though none of that might be interesting, or many of those might not be interesting. Same thing with Dunn-Sidek. Bonferroni and Dunn-Sidek aren't post hoc comparison tests. They're corrections for planned comparisons. You shouldn't be exploratory Bonferroni correcting for anything. But that's what SPSS is going to do. And what's going to happen is just, I mean, if we do this, unless you're doing this because you already have a game plan and you're just doing this for convenience, what this is going to do is it's going to give you a whole bunch of tests, right? If I go through and do the same thing for my unordered means where I've got 8 different comparisons, I'm going to get this, right? Looking at all possible comparisons between all ratings for all vignettes, right? And it's going to encourage you to just go on a fishing expedition, find the ones that are different, and then come up with some post hoc explanation for why those are different, right? And so be very, very careful. Again, you can do this as a means of efficiency, right? But recognize that what you shouldn't be doing is just going down through and listing things. I reviewed a paper where someone did this and then just reported them all, even though, I mean, there weren't quite this many. We've got 6 possible unique comparisons. We've got 12 here, right? Half of these are just redundant, right? Someone just went through and just listed all this stuff down. That's not useful, right? That person was either careless or was not clear on what they were doing anyway, right? So just wanting to know what these are doing, where these are coming from, so we can do this in an effective and meaningful way. Other thing we can do with our, if we really want to do all possible pairwise, we can apply two-key correction, okay? Two-key correction is easy to do by hand, right? And it's nice because with our one-way designs, all possible pairwise comparisons are interpretable, right? I can, if I wanted to, in my unordered means, I could compare ratings for any two vignettes, and that's an interpretable result. I probably don't want to do that and work through 28 of those, but I could, right? And so what we would do if we wanted to two-key correct, right? What we could say is, okay, SPSS won't give this to you, but we can do it quite easily. If we go through and we say, okay, grab your two-key handout here. Let's say for our VDI scores, right? So we've got 4 of those, right? And so what I want to do is, let's say I do, for some reason, want to look at all possible pairwise comparisons of VDI scores across these 4 assessment points, right? And so what I would do then is I would identify my critical Q based on my two-key table here, right? So how many means do I have? 4 in that set, right? So if I look at my two-key table, and I look at 4, and I look at, and I had, how many people in that sample? 231. Yeah, okay. So my degrees of freedom for any pairwise test is going to be, if I get 231, it's going to be 230, right? So it's not infinity, so I'm going to not, you can choose infinity, but I'll just say 120 degrees of freedom, given that that's sort of what's available on my list here. So I'm looking at the number of means that I have is 4. I'm going to, so we just guesstimate at 120 degrees of freedom, would go down through, and I find a critical two-key value of 3.69. Q critical, 3.69, okay? People see where I'm getting that from? Okay. So then what I do, if I can go through, what I can do is I can calculate now a critical T based on my two-key statistic here. And if we go back through, take a look at some of your 50, 60 notes, remember that our T statistic and our two-key statistic hold a direct relation with one another. And I can take and get my critical T, if I take my two-key correction for my corrected Q statistic, and I divide that by the square root of 2, that now gives me a new critical value that I can use for all of my assessments. So with 120 degrees of freedom, what's my critical T going to be just if I were at alpha equal 0.05? What's it going to be very close to? So if I were to just run a independent sample t-test with 120 degrees of freedom, or a paired sample t-test with 120 degrees of freedom, what would my critical value be very close to? 1.96, right? We're seeing that there's an upward correction, right? We're increasing the threshold in order to claim significance with our corrected test statistic here, right? But what we can now do is we can go through, and I could run, if I wanted to two-key correct, I could run all possible pairwise comparisons within this set and compare each one of those test statistics to my new critical value, right? And if it's significant, then I just say this is significant at two-key, or at alpha less than, with a two-key correction, alpha or p less than 0.05. Okay? With two-key, you don't get a specific p value for the correction. We're just saying, is it statistically reliable at alpha less than 0.05? Or if you take it and flip over to the next page on your handout here, we've got, this is your two-key table for alpha equal 0.01. We could do the same thing, and we could two-key correct for at alpha equal 0.01 if we wanted to, right? So again, if we wanted to do this, this would be something we could do fairly easy. I mean, or if we think about with our unordered means, our Q critical for that example is going to be 4.36, and so T critical, there if we take 4.36 divided by square root of 2, someone tell me what that is.
It's 4.36.
4.36 divided by the square root of 2.
I got 3.08.
What is it?
3.08.
3.08. Okay. So you can start to see this is a huge correction over 1.96, right? And if we were going to go through and test all possible pairwise comparisons in our unordered means, right? This is a really high bar to hit, right? But what we're doing is we're correcting for a ton of different comparisons, because with our post-hocs, we're just going through and we're just looking at whatever. Right? So we can do, now this starts to get complicated when we start to add in a between subjects factor. So when we're looking at between and within, are all possible comparisons in our factorial designs interpretable? No, they're not, right? So if I want to look at group 1 on time 2 and group 3 on time 1, there's no reason to compare those because that doesn't make any difference, right? And so things start to get tricky with Tukey. We kind of work with an adaptation with this, but easy to do in our one-way design, starts to get more difficult with our mixed designs. Yeah.
So for corrections, if we had like 2 different types of repeated measures and numbers we were looking at, would we use the same correction for one to make correction for the other test, or we would have 2 different corrections?
I would probably say, all right, for this, so let's say I've got this outcome for this repeated measure, and then I've got another model for a different model. I would probably just say, look at correct for the comparison I'm making in this model, and then do the same corrections for the comparison in the other model, right? So if I had 4 contrasts in this model that I was going to look at, I would just correct for the 4 in that model, and then over here I would correct for the 4 in that model, as opposed to overall correcting for 8. And this is where we get into families of tests versus all the tests that you would make, right? If you think about it, it wouldn't make sense if you were to go through and write a publication and say, these are all the significance tests that I made within the context of this project. I'm going to take alpha and divide it by that number of tests. That wouldn't be reasonable, right? So you tend to think about things in families. That's a good question. Other questions? Other thing you could do that I'm increasingly a big fan of is this Benjamini-Hochberg test. We talked about this last time, okay? What we're looking at with Benjamini-Hochberg is a false discovery rate, okay? The idea is that with our family-wise error, we're concerned with the probability of committing one or more type 1 errors over the course of a set of tests. And it assumes that all of our conclusions are wrong if we make even one type 1 error. Benjamini-Hochberg takes a little bit different approach in asking what percentage of our significant effects are likely false positives through and talk about things. And so what we would do, remember with the Benjamini-Hochberg, is we go through and we run our comparisons, right? The comparisons that we're going to run. And in this case, if they're all possible comparisons, let's say with our depression means, we've got 6 different contrasts that we run, right? We contrasted 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4, right? So we've got 6 pairwise comparisons, right? So what we would do is we would go through and calculate a unique p-value for each one of the, or a unique criteria for each one of those tests. So we would say, and the criteria for each test is going to be an index value over the number of tests multiplied by alpha. Okay? And so in this case, I is a test index, K is the number of tests, and what we're going to do with Benjamini-Hochberg is we're going to order our contrasts in order from our smallest test statistic to our largest test statistic. Okay? So I went through and actually ran repeated measure paired sample t-tests for the depression set, looking at 1 versus 2, 1 versus 3, 1 versus 4, 2, 3, 2, 4, 3, 4, right? Calculated a test statistic, our t-statistic, for each one of those, so this would be all possible pairwise comparisons within this ANOVA, this one-way ANOVA. And then what we do with Benjamini-Hochberg is we just line these up, right, so that my lowest value is first, and then each increasing value, right? Now here, this is the p-value for those tests, right? Because they're got a billion people and they're all hugely different, right? But in theory, what we would do is we would say, all right, so my lowest value was comparing scores at week 4 versus week 6, right? Gave me a test statistic of 9.28. Just as a per comparison, right, that's clearly significant. But my index for this is 6. So I take 6 divided by 6, the number of comparisons I'm making, multiplying that by my alpha level. So if I take 6 divided by 6 and multiply it by 0.05, you just get 0.05, right? But then my second lowest one is 10.36, right? This is the comparison of 2 and 3. So here, I'm going to take 5 divided by 6, multiply it by 0.05, and I get a criteria of 0.042. And so on and so forth, 0.035, 0.025, right? So as we keep adding additional tests, my threshold gets increasingly stringent as I'm working down, okay? Now in this case, these are all clearly meeting threshold for statistical significance, right? But if we were to run this with our unordered means, it would be a much larger table, right? But at some point, we'd probably, up here, would likely find stuff that wasn't meeting our criteria, maybe farther down we would. And so the Benjamini-Hochberg, it's a different approach, but it's nice. It kind of takes a look at things a little bit different. How sort of talks about this in his chapter. I can't go through and take a look. This would be basic procedure for going through and taking a look, and instead of no correction or like a 2P correction, going through and taking a little bit different approach to order things up. Okay, spreadsheets are nice with this, right? If you sort of dump this into an Excel, you can start to work through this very quickly. Okay. Questions about Benjamini-Hochberg? All right, cool. So effect sizes, right? We went through and we calculated some effect sizes here for our one-way designs. Again, our concern is what do we use for our standardizer, right? Some different approaches, ways we can go through and take a look at things. Now here, we had things were pretty straightforward, but with our repeated measures designs, things can get kind of tricky, okay? One thing that Howell will talk about is advocating the use of standard deviations of the means of participants' baseline scores. Now, in some types of designs, we might have multiple baseline assessments, right? If we've got, say, we go through and we get people at their first at intake, and then we've got like another week follow-up where we haven't done anything, we take that, take a measure there and then start people into treatment or something. Or we've got some sort of experimental design where we have people just sit and do nothing, and then we have them watch some neutral stimulus, and then we start into whatever manipulation we're going to do. So we kind of got two different baseline assessment points here. One thing that Howell makes an argument for, and so think about this as kind of like a glasses delta, except you've got multiple baselines in this design, is using the standard deviation of participants' total baseline scores. So this is our set here, and what we want to do is we've got baseline 1, baseline 2, and then we got baseline 1 is A, baseline 2 is B, and then D is something that's happened sort of down at the end of the manipulation, right? So what we want to do is we want to compare the combination of our two baseline groups to our outcome, right? So we can run our contrast, that's fine and easy, we know how to do that, we've gone through it. But if we want to go through and calculate our effect size for this, what we could do is we could go through and calculate the mean for our baseline assessments for each one of our participants, right? And so if we would take the mean of our two baseline assessments for participant 1, it's going to be the average of 2 and 4 is going to be 3. For person 2, it's going to be 11, the average of 10 and 12. For 3, it's going to be 22 and 29, going to give us 25.5. 30, 31 is 30.5, right? So we've gone through and calculated the average score for each individual across the two baseline assessments. And then what Hal is advocating for is then what we do is we go through and we take standard deviation of the average baseline score. So what we would do is we'd take the standard deviation of 3, 11, 25, and 30, and we take the standard deviation, use that as the standardizer for our effect size. Okay? So again, what we wanted to do, because we're going to get some differences in terms of standard deviation at baseline 1, standard deviation at baseline 2. What Hal is doing is saying, okay, what we're going to do is take the average of those scores and then create a baseline there. So if we run into a situation where we have multiple baselines, this might be something that you might want to take a look at. Other things that we can do, pooled standard deviation of all the cells included in our contrasts, right, which is what we had kind of done here before, okay? You take the pooled standard deviation of all the cells in the design. These two for our, when we calculated so this is what we did for when we were looking at differences in pre-post, right? We kind of just took the average at time 1 and time 2 and just ignored, or at pre and post and then ignored everything in the middle. That's kind of what we would be doing here. But if we had more contrast with more cells involved, we can do that. Here, in our unordered means, right, we ended up taking the pooled variance of all of our repeated measures, just because we had 4 at the front, 4 at the back, and then compared those two. Essentially, we did this, but it ended up being that exact same thing, right? So different ways we can go through and approach standardizing our effect size, okay? And so this is important. There's just so many different ways to go through and calculate your effect size. Always want to make sure that you're telling people what you did, how you calculated that effect size, providing some justification for why that made sense to you to do it that way. Okay. All right. Repeated measures on effect sizes, confidence intervals on repeated measures effects. We've got different ways of going about things, right? We talked about why, if we're going to calculate a confidence interval around a repeated measures effect, we have to make sure that whatever variance estimate that went in the calculation of our test statistic is also the variance estimate that's going into the standardization of our effect size. This is true for all confidence intervals around effect size that we make. It just ends up being a more obvious deal when we're talking about repeated measures effects, because we'll end up with a point estimate. If we don't do this in a repeated measures design, we'll end up with a point estimate that doesn't fall within the confidence interval that we've calculated. If we screw around with this in between subjects, it still generally will fall in there. I just wanted to be careful with this. We're not going to worry about calculating confidence intervals around repeated measures of effects, although we went through and talked about how to do that in the previous example. Know that you can do that. It's a little bit tricky, but come talk to me if you want to go through and do this. We'll make sure that you're getting things squared away appropriately. Okay. All right. So those are our one-way designs, right? These are pretty straightforward because all we've done is we've gone through and we've said, okay, here's one group of people, and we're just going to measure those on a number of different time points. Those are not straightforward, but kind of limited in what we can do with these. What often we want to do with these, and again, this is the bread and butter of theses and dissertations and things along these lines, right? Is we're looking at maybe having one or maybe two between subjects factors. So we've got different groups that we've gone through and collected repeated assessments across a number of different time points. What we've got now is a mixed subjects design, and these can get pretty tricky, okay? These are, again, very powerful. These are interesting designs, but all of a sudden we've got things being partitioned in a lot of different areas. We want to make sure that we know what's going on, where things are happening, okay? So in this example, we have a 2x3 in this table. We've got a 2x3 mixed factorial design. We've got one between subject factor with 3 levels. And then we've got one within subject factor with 4 levels, right? So we've got some grouping level, right? So we've got some group of individuals who we've randomized to conditions. So we've got 3 levels to our condition, and then we've made 4 repeated assessments over the course of our study, okay? And so our questions here, right? We're going to get a main effect of group, right? And the question is, do scores differ across levels of factor A after we collapse all of our repeated measures, right? And our output, this is going to give us our between group differences, right? So if we take a look here, right, we have group mean, the mean of group 1, collapsing across repeated measures, mean of group 2, collapsing across repeated measures, mean of group 3, collapsing across repeated measures, right? So 1, 2, 3. And what we're doing here is our question is collapsing across repeated measures, do we see aggregate differences across our groups? Okay. This is often not an interesting piece of information within these designs, but it's going to give us something that we can test, right? We can also ask, do scores vary across repeated assessments for factor B collapsing across groups? So do we see, if we ignore groups, do we see differences in our repeated measure over time, right? In this table, this is going to be, do we see differences in our repeated measure for time 1, time 2, time 3, and time 4 if we ignore group? Okay, that's going to be our main effective time or assessment, whatever our repeated measure is. And then we have the question, do our repeated measure scores vary as a function of group, right? Is the pattern of means that we see across repeated measures different for group A versus group B, B versus group C? Okay, and what we're looking at here then is differences across our individual cell means, right? Do we see a different pattern of effects for one group versus another group as we work across repeated measures? Okay. What are we talking about? What is this question? It's a moderation question, right? Anytime we get an interaction, this is a moderation question. This is saying, does group membership impact the pattern of means over time? And so if we're going to break this down, okay, and I gave you a sheet that goes through and sort of helps you sort of get a sense for how to partition all this stuff out, right? But our sum of squares total here, this is just going to be the sum of the squared deviation scores, looking at individual people's scores, individual scores, deviation from the grand mean, right? So this minus this, this minus this, this minus this. Right, this is all the variability in our set that we're working with. Okay? We also, again, just like before, we're going to participate, take that total, we're going to section it off. We're going to have between subjects variability and within subjects variability. The between subjects variability is just sucking out all the individual differences, right? This is what makes our design so powerful. Okay? And if we look at our between subjects, this is going to be our individual participant means minus the grand means, okay? So this is going to be our deviations from our individual, participants collapsed across time, subtracted from our grand mean, squaring those deviations and multiplying that by the number of within subjects assessments that we have, okay? That's taking all the individual different stuff and sucking it out, okay? But then what we've got is our effective group, right? Our effective group is going to be our group mean minus our grand mean, right? So we're going to go through and take the deviation of our group mean minus our grand mean, group mean minus our grand mean, group mean minus our grand mean, and multiply those squared deviations, the sum of the squared deviation scores, by the number of people we have per cell and the number of within subjects assessments that we've got, okay? And so functionally what this is doing, think about this as its own separate ANOVA, right? We're going through and running a between subjects ANOVA off to the side here. We're taking all the variability that we would attribute to one-way ANOVA and just sucking all that out of the total variability going on here, right? And so here's our, this is going to be our main effective group, right? This is going to answer, this effect is going to answer the question, do scores differ for factor A across the repeated assessments, right? But then what we've got, we've also got our within subjects over here, right? Our repeated measure is going to be our number of, or we're going to take our mean of our repeated measures minus our grand mean, take the sum of those squared deviations, multiply that by the number of, or cell sizes times the number of groups. That's going to give us our repeated measures. Our cells, this is again is a computational thing. This is going to be our group repeated measure, deviation from the grand mean, and then with subtraction, we're going to get our interaction here, right? So again, what we're doing is we're going to section this off, and this is going to start to become important when you're working through that Bakeman article and trying to figure out where these things are going, right? But what we've got is we've got a between subjects thing, right? And that's going to be just our own between subjects design, and what we're left over with is going to be our repeated measures factor, and so we're going to get a main effective group collapsing across repeated measure. We're going to get a main effective repeated measure collapsing across group, and then we're going to get our group by repeated measure interaction that's going to tell us whether or not we see differences in patterns of means across different groups. Okay? So things start to get kind of funky, but again, use that sheet to go back through and take a look, wanting to get a sense for where this different stuff is falling out. Okay. Questions about this? All right. So for our mixed designs, okay, we've got a between subjects assumptions, we've got within subjects assumptions. For our between subjects assumptions, we're assuming normality, right, and asterisks. Why is this asterisked, Angeline? There's a lot of asterisks. It's a lot of A vowels.
Because it may not be normally.
It may not be normally distributed. Do we care if our observed values are normally distributed?
No, as long as we assume, like, it approaches, as long as the population is managed.
Okay. What's the actual assumption in our grouped designs? You know, Steph?
The sampling distribution is what we have.
The sampling distribution, right? And so we know that the sampling distribution is going to approach normality, and this is what you're getting at. When our observed scores are normal, or excuse me, when the population distribution is normal, or if we have reasonably large cell size, right? Cell sizes above 30-ish, right? We know that even if whatever we're looking at in the population has a kind of skewed distribution, the sampling distribution of that is going to approximate normality very quickly if we've got large samples or reasonably large cell sizes. Right, so sampling distribution is going back. This is our homogeneity of variance assumption that we spent time in 50-60 talking about. We're assuming that based on our data, we can reasonably assume that the variability of scores across these different populations is going to be roughly equal. And with our within subjects, this is where we're assuming our normality of our distribution of sample means, right? Homogeneity of variance across intervals, right? So we've got here homogeneity of variance across groups. Here we've got homogeneity of variance across repeated assessments. And then we have our sphericity assumption here. Okay. So we've got more things to think about in terms of our mixed factorial designs. So we want to just make sure that we're accounting for some of this stuff. Okay. So we've got a couple of different examples. We're going to use the same sets that we have used before, so we're good on that, right? But what we're going to do is we're going to start to add a between subjects factors, but within subjects factors that we've already gone through and taken a look. So for our ordered means, for our inpatient depression, what we're going to do is we're going to go through and we're going to still have our 4 repeated assessments, right? But what we're going to do is we're going to look at these, actually, surprise, you didn't know this. This is a big reveal, right? So you all get very excited. Turns out we're actually looking at 3 different programs, right? And so the question here is we've got people in 3 different programs within this unit. We're following along the same assessment points, and we're wanting to see overall, do depression scores vary over the course of 6-week hospitalization, right? Sam, what is this question mapping onto in terms of our output? What's that? Yeah, this is just our main effective within, right? So regardless of what program people are in, on average, do people in our sample show different patterns and means over across repeated assessments? Okay. And then do overall depression scores differ across treatment program? What are we looking at here, Katie? Are between, right? So regardless, and this is why this often doesn't make a lot of sense, particularly with this. Basically, it's saying over the course of treatment, if we collapse and just take everybody's average score in each one of these, do we see one group, or do we see differences in average scores collapsing across treatment across groups? Right? So basically, we're saying if we take the average BDI score across the 4 assessments, do we see groups differing in that? So that's, and this is not really a meaningful question necessarily, right? But we're going to get an effect looking at, on average, do we see differences in groups, in average BDI depression score across groups? And then our last one, does the pattern of depression scores vary based on treatment assignment? What are we asking here, Lauren? An interaction, right? Do we see the pattern of reductions? Or is the pattern of reductions in depression means over the course of treatment, are they different for one group versus another? Do we see differences in how these patterns are working out? Okay. So we've got that with our depression scores, and then with our unordered design, again, we've got, here we're going to limit ourselves to, just to make things more manageable, just our 4 trauma-related ratings, right? So ratings of willingness to maintain friendship after someone's been in a car accident, after combat, after sexual assault, and after a natural disaster, okay? And then what we've got is because we went through and we classified people based on their beliefs about trauma, right? Do people generally think that people who've been exposed to trauma are screwed up, right? And they're dangerous, and they're could go crazy at any moment, right? We've got people who we've identified in this negative group. Then we've got a benevolent group, right? Think about this as being nice, maybe a little bit paternalistic, right? But no, they're going to be fine. You know, they need support, they need help, you know, that type of thing. And then a third group that's marked by different types of interpersonal concerns. Like, yeah, they're going to be fine, but I don't know that I would want them watching my kids, or I'd be worried about dating someone with a trauma history, or I don't know if I'd want to work with somebody with this, you know, these types of things, right? And so we've got 3 different groups there, and looking at differences and looking at the people in these 3 different groups, looking at their willingness to maintain friendship across these 4 different scenarios, okay? And so we've got our first question, does willingness to befriend vary within a person across different traumatic events? Alex, what are we looking at in this first question? Yep, this is just our within, right? Collapsing across conditions, right? do we see different ratings of friendship across these repeated assessments, right? So it doesn't matter whether or not we're talking about someone who's been exposed to combat or whether it's someone exposed to motor vehicle accidents. It doesn't make a difference if we're ignoring group membership. Okay. Angela, what about the second one? Does overall willingness to befriend differ on belief profiles? That's our between. And in this case, it's actually kind of interesting, right? So if we just say on the aggregate, regardless if it claps across the specific vignette that they're talking about, do we see that these groups are different in terms of their willingness to provide friendship if we sort of just kind of collapse across individual vignettes? Here, our between is actually kind of interesting, right? Because it says, well, it doesn't really matter who we're talking about. This group is tending to report higher ratings or willingness to provide friendship than this other group, right? So in this situation, the between is kind of interesting, right? And then finally, here, does belief profile impact pattern of friendship ratings across traumatic events? Do we see different ratings of whether or not people are willing to provide friendship depending on kind of what type of trauma we're talking about? Okay. People get a sense for how we're sort of layering this in, doing some between and within? Okay, so let's go through and jump into let's look at our belief rating set. We'll start there. So here we got our belief rating set. One thing we want to do is we'll go through and sort by class. It looks like we were missing scores here, right? I want to go through and get rid of those before we start, right? And then I'm going to file, scrap one, something like that, just so I'm not losing information. Okay. So what I want to do here first is I'm going to go through and run some descriptives. Right? And what I'm going to do is I'm going to look at descriptives for French, their motor vehicle accident, combat, assault, and disaster. Because those are my trauma-related things that I'm worried about here, right? And then I'm going to go through, I'm going to say options. I'll look at skew and kurtosis, and I'm going to hit OK. Hit save standardize. We won't go through all of it, but this is going to give me my standardized values. I'm going to hit paste. Okay. Before I run this from my screen, what do I need to take into consideration? Should I just run descriptives for the whole set? What am I missing here? I got different groups, right? So before I run this, I'm going to go data, split file. I'm going to take class, I'm going to organize. Actually, I'm going to hit compare this time. I'm going to paste here. Okay. For this screening, right, I want to go through, because what could happen is values that seem reasonable for my benevolent group might, or reasonable for my negative group might not be reasonable for my other groups, right? So what I'm going to do first is when looking at this stuff, remember, same thing as our between subjects, we have to split our file. We have to break this up before we start going through and taking a look at stuff. So I'm going to sort and split my file by class, and then I'm going to run through and take a look at my descriptors here on the front end, okay? So I'm going to go through, and I'm going to run this. And I get a lot of stuff here, right? But what I've got is my distributions for my different scores for my negative group, my benevolent group, my interpersonal group, right? For each one of my 4 vignette ratings. Okay. So if I'm going through and I'm taking a look, right? how are these ratings looking in terms of their distributions? What do you think, Sam? Are we excited about these distributions?
No.
No, we're not, right? These are pretty ugly, right? We've got, I don't know, kurtosis of 17. That seems problematic. Skew over 3, right? Close to 4, right? If we were to go through and look at the actual distribution of these scores, things would look pretty gross, right? And so I would want to go through and take a look at some of this stuff. Now, what's my saving grace here in terms of my distributions? I got pretty good cells. Are my cells equal? No, I've got a clearly unbalanced design, right? Because I didn't randomize these, this is pre-existing stuff, right? So I've got an unbalanced design, but my smallest cell here is 44, which is still gonna be okay, right? Other thing too, my ratings are from 0 to 8, so even if I have outliers, they can't be huge out, I mean, they can only be, I can't have like a score of 1 million in here that's dragging things way out, right? So these are some things that I want to take into consideration. But the tricky thing with this is that we need to go through, and when we're taking a look at our variance assumptions, our F-max gets a little complicated, right? Because we need to dig through and we need to take a look at homogeneity of variance across conditions and within and across assessment points, right? And so what ends up happening is things get a little bit tricky. So what we want to do here is we've got, we'll say we've got neg, then an inter, right? And then we've got R1, R2, R3, and R4. Okay. So if I go down through and I take a look at my, and I won't worry about variances here, but that's what we need to be looking at. I'll drop in standard deviations just because it'll be easier to do. What I need to do is for my negative class, I need to go through and write for my first rating is going to be 1.023, right? Yeah. 1.730, 1.146, 1.039. And for this, it's going to be 748, 1.054, 0.757, 795. And here, 658, 0.881, 0.787, 0.784. So we've got a matrix of variances to be aware of here, right? And so what we want to do, so what do we use to compare these? What's the test statistic that we talked about using? The F-max, right? So what we can do is I can go through and calculate now, again, remember these are standard deviations. These aren't, I would need to square each one of these to make sure that they're variances, right? So, because a little bit of difference between two standard deviations becomes a lot of difference as soon as you turn those into variances, right? But what we would need to do is calculate an F max to look at for our first rating, for our first vignette, variability. Do we have large discrepancies in the variances across groups for our first vignette? Do we see large variances across our second vignette? We see large variances across groups for our third vignette and our fourth vignette. So each one of these are Fmax values, right? But then we also need to think about for our negative group, do we see large differences in the variance across individual vignettes? So I've got an Fmax here, I've got an Fmax here, and I've got an Fmax here. Okay. I see Sam smiling, he likes this. Okay. You know what happens? You know what happens when we add a third factor? We get a three-dimensional space. And you got a cube. You got a cube of variances. It's exciting. But the thing is remembering that we've got a complex design. We've got between and within stuff to keep track of. And so in this scenario, we would want to go through and see what is our Fmax for within subjects, right? So for each group, differences in variability across ratings, and then across ratings, differences in variability, or within ratings, difference in variability across groups. And what we're going to be looking at is looking for that Fmax statistic. Now this is where, again, we can start to get into problems if we see variability, that Fmax ratio getting to and exceeding 3, right? If we have unbalanced designs, do we have unbalanced designs? Yeah, we have a clear unbalanced design here, right? And so this is where things start to get a little bit tricky, wanting to go through in your initial screening, start teasing some of this apart, right? Is there evidence of differences or problems, right? You might say, well, for the combat, ratings for the combat vignette, we're seeing some level of differences in variability in ratings across our negative, our benevolent, and our interpersonal group. Or we might say for our benevolent group, we're seeing potential violation of homogeneity of variance across our sexual assault and our disaster groups, which is giving us a high Fmax, right? And so there's just a lot of things to kind of take note of, because then this starts to impact sort of what we should be doing in terms of teasing apart some of our effects that we find. Okay. Questions about this? So again, in our screening, we would go through and we would look at outliers, and we would look at our distributions, and we would make judgments on whether or not those are things that are important or not important based on sort of features of our design and things along those lines. We want to take a look at our variability assumptions here with some of this stuff. But once we get that all done, what we're going to do is we're going to go through and we're going to run our actual analyses. Oh, yikes. Okay. Well, get as much done as we can here. So we're going to go general linear model. We're going to go down and quick repeated measures. Okay. And so our factor here, we'll call it rating. We've got 4 levels to this factor, add. Okay. We're going to find, just as we did before, we go motor vehicle accident, combat, assault, and disaster. Right? Because those are our 4 trauma ratings we want. But then what we're going to do is we're going to go down to class, and we're going to drop class into our between subjects factor. Okay? This is going to tell it, all right, what we're going to do is we're going to model a within subject effect for rating, a between subject. Okay. Then if we go to contrasts, and then we can, you don't have to worry about this because this is unordered means, right? So we're not worried about getting anything going on there. Plots, what we'll do is we'll say we want rating on our horizontal axis and classes separate lines, right? So this will give me a different pattern for each one of my classes. We'll add that. We'll say continue. Post hocs. This is where you could start looking at differences in across class. I'm not going to have you do that because this is just throwing in a bunch of stuff that's not going to be necessarily useful here. So we're going to, basically it's going to start contrasting across individual repeated measures, differences across class. We're not going to worry about that here. Say we won't do that, but then in terms of options, right, we'll ask for marginal means for class rating and the interaction. We'll ask for descriptives, estimates of effect size, and, not transformation, and homogeneity variance tests. We've gotten an error before because it's not going to give you homogeneity variance tests if you don't have a twin subjects factor. Now we do, so we can go through and add that in. Continue, and then hit OK. Oh, whoops. Anybody know what I did? It's still split. All right, go through. Measure, define. There we go. All right. So what we've got here is we've got, again, always wanted to go through and take a look to make sure that our, we were looking at the repeated assessment that we're trying to look at here, right? So we've got rating 1 is accident, combat, sexual assault, disaster, okay? So that's good. We've got things loaded in there that we want. We're looking at our between subjects factors. This is given our cell size. We've got clear differences in our cell size. We've got an unbalanced design. That's something we want to take a note of, okay? Then we've got our descriptive statistics, right? We kind of ran these before, but this kind of packages it up nicely. Here we can go through, take a look at means and standard deviations. Now, if I'm going through and I'm taking a look at just eyeballing these, and am I excited about my prospects here? Now, that's a lot of 7s just running down that line, right? But again, we've got a really powerful design, and so we can start to tease apart very subtle effects here. Okay. You'll see boxes M, you can ignore that. The quality of covariance stuff, we're not too terribly concerned about this, so don't worry about that. Got our multivariate tests. Again, that's just a different way of approaching some of these analyses. We're not going to worry about that. We're going to get to our test of sphericity. Are we concerned about this? Nope. We assume that we violate this anyway, so we're going to ignore that. All right. And then we get into our test of within subjects effects. All right. And now we've got something that's looking a little bit different than what we had before. So here, we've got our effective rating, right? What does this correspond to, Alex?
The test of within subjects?
Yep, this is just our within subjects test, right? And we go through, we can see if we go through, and again, we'll want to use our greenhouse geyser correction here, right? We're seeing that we have a very clear and statistically significant effect, main effect of our repeated measure, right? And we already kind of knew this, right? But what this, well, it's a little bit different than what we had done before. But what this is saying is this, if we ignore group membership, we're seeing differences in average friendship ratings across these different vignettes, okay? If we go down through, okay. If we jump down in our output and we take a look at our, well, skip over the within subject contrast down here. This is our Levine's test, right? This is the Levine's test that we've know and love. But what this is doing, you'll see we have a Levine's test for our car accident, our combat, our assault, and our disaster groups, okay? What this is doing is it's saying across our 3 different conditions, do we have evidence of violations of homogeneity of variance for ratings of our car accident, for ratings of our combat, for ratings of assault and disaster? And it's looking like it is, right? So these, think about this as each one of these F maxes that we calculated right here, right? It's saying that we've got violations of Levine's across each one of these. Now we've got a lot of people in this sample, but still looking like we can't assume equal variance in the ratings of each one of these vignettes across our groups. Right, so we're going to want to take that into consideration. Right? But if we go down through and we take a look at our tested between subjects effects, we're seeing that we have a main effect of class. Right? Katie, what's this telling us? Mm-hmm. Yeah, within the context of these data, what's that telling us? Yeah, right. So regardless of if we collapse across individual vignettes, we're seeing that we have differences in average rating across vignettes across our different classes, right? So this is saying within the context of this study that our negative class, people in our negative class are rating vignettes differently on average than benevolent or our interpersonal class, or somewhere in there, right? Our negative, our benevolent, and our interpersonal classes are rating these vignettes differently. There's some difference in average rating across groups, collapsing across individual vignettes. Okay, and so here we can see that between subject effect right here. Now, if we go back up to our test of within subjects effects, okay. We also have our rating by class interaction. This is our within and our between, by between interaction effect. And we see that if we take a look at our greenhouse geyser corrected statistic, we see that we have evidence of a significant interaction of within by between. Candace, what does this tell us?
Sorry, what?
So any thoughts on how we might interpret this interaction effect? So we've got an interaction, a significant interaction of belief class by vignette rating.
Is that all we know?
Yeah.
Oh, well, I don't know. Broadly, you can say that belief class rating depends on the other thing that you said.
Yeah, no, perfect. And broadly speaking, that's all we're looking for. This interaction is just saying that the pattern of friendship ratings across these individual vignettes differs by belief class, right? So our grouping variable makes a difference in terms of how these patterns of means fall out, right? And if we go down through and we take a look, okay, one is our motor vehicle accidents, 2 is our combat survivors, 3 is our sexual assault, and 4 is disaster. Okay. Angelina, what's going on with this interaction here? Just eyeballing that plot, what does it look like is going on?
Individuals with a negative belief profiles are different from the ratings from the other 2 profiles.
Right. So our pattern is looking pretty different, but it looks like the people who we've classified as having negative beliefs are really, I mean, it's still high, but we're seeing a marked reduction in their willingness to provide friendship, specifically to survivors of combat trauma relative to other people, right? And so if we're looking at this pattern of means, we can say, again, we saw that main effective group, right? Or, well, let's say, start with our main effective repeated measure, right? Our main effective, our repeated measure is saying that the collapsing across groups, people's ratings of each one of these vignettes are different in some way across the repeated measure. And we can see that pretty easily, right? There's some differences that are going on in terms of mean. So if we ignore individual groups, we can see that ratings for accident survivors are different than combat survivors, are different than sexual assault survivors, and different than disaster survivors, right? So if we were to just take the averages of each one of these and just plot that out, looks like we're seeing differences there. We're also seeing here differences in group, right? Our main effective group says that if we collapse across, if we take the average of all these ratings, we're seeing differences in those means across each one of our different groups. And again, if we were to take for our benevolent and for our interpersonal groups, and we were to just take the average across ratings, right? We can see that our negative group is reporting or providing lower levels of willingness to maintain friendship than the other two groups, right? But then our interaction, what our interaction is telling us is that the specific pattern of friendship ratings across these vignettes is different across our three conditions, right? And what I'm seeing here, and what Angeline points out, is that it looks like our negative and our our benevolent and our interpersonal groups, they're looking about the same, right? These ratings are right on top. We get a little bit of a difference in terms of natural disaster. That's probably just fuzz, right? But what we're seeing, and even the rating of for our negative group, and it's kind of following the same pattern for accidents, sexual assault survivors, and for disaster, right? But I'm thinking it's this combat survivors, right? Within this group, right, we're seeing a much larger discrepancy between the ratings for combat survivors versus other groups than we are in these other means. It's still kind of seeing the same thing up here, but much more pronounced in this group, right? And so this is where this between by within interaction is coming into play, right? It's saying that the specific patterns and means that we see across repeated ratings of different vignettes is different for each across our belief conditions. Okay. And so then what we would need to do is think about how do we go through and start teasing apart things. Now this is pretty obvious what's going on here. I can see, just eyeball this and kind of see where the action is going on. But if I were to go through and follow this up, would want to have a plan for how I'm going to go through and start pulling this stuff apart. All right, folks, thanks for hanging out with me for an extra 10 minutes here.